Good morning. Today my lecture is on string matching algorithm. So let's understand what is utility of the string matching. So actually, if you know that text editing program like Microsoft Word, so we need to frequently find out occurrences of a pattern inside the text. Sometimes we are using Control F to check whether a pattern is occurring in the text or not. So here in this kind of editor, we assume that entire Microsoft Word is a document text, and the pattern is the keyword which we are looking for in that text. So there are many efficient algorithms for this problem, and we call them as a string matching algorithm. So we know that it has many applications, for example in DNA searching, information retrieval, and so many places. So in order to get matching of a pattern inside text, we need to define valid shift. So what is valid shift? So suppose text is represented as 1 to n of length, its length is n, and pattern is represented from 1 to m, its length is m. So generally we require that m is always less than or equal to n. Pattern length should always be less than or equal to n. So we further assume that the symbols of text and patterns are taken from some finite alphabet sigma. That finite alphabet sigma can be decimal integer, can be any string, can be any alphabet, right? So what is what is formal definition of string matching? We'll look into it later on, but generally what is objective of the string matching is to get all valid shift such that pattern 1 to m actually is basically equal to text s plus 1 to s plus m, where valid shift can be from 0 to n minus m. Look at here, like see, this is your text and this is your pattern. What will happen if you look at s equal to 3 valid shift? So this s equal to 3 means this is 3 plus 1. That means if we represent this by 1, 2, 3 and this is 4, so that means 4 plus 1 up to pattern length. So 4, 5, 6 and 7. So this should be equal to pattern 1 to m. Exactly this is same. A and A equal, B and B equal, A and A equal, A and A equal. That means this s equal to 3 is a valid shift, right? So what is valid shift? Any integer is said to be a valid shift if actually text of s plus 1 2 up to and so on s plus m is basically equal to pattern from 1 to m. So not otherwise it will be invalid shift. So there are many algorithms to find out a pattern inside the text. We know first algorithm, which is very basic, is like a naive algorithm, which we call it brute force. Second algorithm in this category is Carp algorithm, which was invented in 1987. And third algorithm in this category is Knuth-Morris-Pratt, which was invented in 1977, and next category is Boyer-Moore 1997. And there are many inventions on this bit parallel and other kind of string matching algorithm. Research is still going on, since this has many applications in real life. Even our Google is using string matching algorithm to find out a particular pattern inside the document, right? So this has many applications. So as per our syllabus, we are having only naive, Rabin and Knuth. So I am going to discuss only top 3 algorithms. Rest will be discussed in the next lectures. So actually what is idea behind the naive based algorithm actually? So in this naive algorithm, we try all the valid shift, like see, if we try s equal to 0 and consider this as a text and consider this as a pattern, right? So if we say s equal to 0 means that this one, 2, 3, 4, 5, 6. That means if we take s equal to 0 means 1, 2, 3. pattern length is 3. This is matching, yes, it is matching, but there is mismatch on S equal to A. There is mismatch. So that means S is equal to 0 is not a valid shift. So what we will do, we will try another one. So let's see, S equal to 1. Yeah, again we are checking A and C, they are not equal. That means there is a mismatch. So they will S equal to 1 is also not a valid shift. So here S equal to 2, we try S equal to 2, all of them they are equal. That means this is a valid shift. Same thing, S equal to 3, it is not a valid shift. Again there is a match on first and there is no match on second. So if we look at here, so actually algorithm is very simple in nature. We calculate length, right, and pattern length is M. So what we will do, we have to check all the valid shift ranging from 0 to n minus m. So after, if S is equal to 0, we will check this whether all the characters of the pattern are equal to the character of the text. If they are equal, that means that particular shift is valid. Just like here, we see that S equal to valid. If they are not equal, we will try another and by changing S. So actually if you look at here, its running time is basically, this is taking n minus m plus 1 comparison, and since this is also of m length, so its running time will be m times n minus m plus 1 comparison. We can say that overall running time of the algorithm is n minus m plus 1. So if you look at here, if we increase m, so what will happen, its running time will always be quadratic in nature. If m equal to n, we will see that n, so like m equal to n, so we have to check all this thing. So basically this is not in like a correct algorithm. As soon as we are increasing, not m equal to n, if we increase the number of pattern length and text length, what will happen, if increase the text length, in that situation m is less than or equal to n, so total time will be like comparison m multiplied by this value. So this is not a very good algorithm. So second category of algorithm is Robin Carp, which was invented in 1987. So actually if you look at here, basically in string matching algorithm, we are comparing particular pattern inside a particular text. But if you look at here in this naive algorithm, this is not very intelligent algorithm. It is not computing, taking any information. So what is happening, it keeps on changing, checking individual occurrences. So this is not very encourageable to apply the naive algorithm. So in 1987, Robin and Carp introduced another category of algorithm, which has almost same running time, but there is a processing time, pre-processing time of big theta m, because pattern has to be pre-processed. It is unlike naive algorithm where pattern need not to be pre-processed. So but you know, it seems that this and naive algorithm have the same time complexity, but it is worst case time complexity, but average case of Robin Carp is better than naive based algorithm. So here actually this algorithm is based on the concept of hashing function, right? This is based on the concept of hashing function. So for simplicity, we assume that all the characters are drawn from the decimal digit like 0 to 9. This is just simplicity, but we can apply it on the characters also. There is no problem. We can make indexing. We'll discuss on it later on. So here it is, in radix of the number system is now 10, right? So what will happen here in this pattern matching? So you know, given this text, we will calculate its decimal value. P denote its corresponding decimal value. Same thing, we are going to have a text n. So if this is of m length, we have to take all this shifting. We have to take its decimal value also, like see, if we range s from 0 to n minus 1, so if we compute this decimal, we can also compute decimal value for individual shift, and we know that if pattern is equal to text of that particular alignment, so definitely their integer value must be same. Just like see, if 1 2 3 4 we are talking about 5, if this is text and we say that this is pattern pattern equal to 3 4, its decimal value is 34, and it is also having another, like see, so its decimal value here also 34. We assume that this is not total integer, so we compare this 34 equal to 34, so they are matching over here, matching it is shift matched at valid shift 2, right? So this is very good method, but we'll see that what is its drawback. So generally, how to calculate integer equivalent of any numbers? It, you know, if we calculate in TS is basically, it is in valid, this one is integer equivalent of s plus 1, s plus 2 and s plus actually s plus m minus s plus 1, s plus m minus 1. So this is actually, suppose you calculate the integer equivalent of beginning number, like see, suppose 31415 is given and next text is going to be 2. So suppose if you know the integer value of this, so how to calculate integer value of next shifting 14152 efficiently? So there is Horner rule, all of you may be aware, it is very good rule. So suppose we want to calculate integer value of 245. So Horner rule is very simple. This will say 5 plus 10 times, then 4 plus 10 times 2. You see, this is actually minimizing the number of multiplication. So this will be t 4 plus 20 and this is 24. So it will become 5 plus 240 and actually this become 245, right? So this is very efficient method which can compute the decimal value of any shift, right? Okay. So to compute the remaining value, we use this formula of the hashing function. So TS plus 1 is 10 times. Actually, this is very simple method. So suppose we have 3, 1, 4, 1, 5 and 2. This is next one. And we know its value already. So what will happen? This is in 10 digit 10. Remove this 3 from here. So 3, 1, 4, 5 minus, we need to remove 3. Here, so 10 to the power 4 and times 3, that means this is going to be removed from this and then multiply by 10. So what will happen? This will happen 150 and then next number is added to become 14152. That is the concept of getting the value of the next text. So next character of the text. So you know this method is okay. We can get the value of the integer value of next shift. But what about if P and TS are very large number, right? So comparing them one by one is becoming very challenging task. So you know Rabin Carp is use the concept of hashing function, right? So this is the definition, TS plus 1. This D stand for decimal radix. And this is h, which is defined as h is congruent to d to the power m minus 1 modulo q. And this is the same where q is going to be chosen as any prime number. There are, yeah. So you know, if you are aware with this modulus system, modulus q, actually if you see this 5 modulo 2 is 1. It is not necessary that only 5 modulo 2 is 1, even 7 modulo 2 is 1, right? So we cannot say that if 2 string have the same modulus, then they are equal. No, you know, look at here, both 5 and 7 have the same modulus, but actually they are not equal because their modulus is 1, their modulus is 1. So, but they are not equal. So, what is actually happening? But on the other hand, if they are on the other hand, that if if modulus is same, right, so they may not be equal, but on the other hand, if their modulus is not same, that means they cannot be equal at all. So actually this is just like going to be used to test whether a particular shift is valid or not, so that it can be rejected. So any kind of shift which is not like valid, we'll see that this is an example of spurious shift. So it is generating many spurious shift. That is drawback of the Rabin-Carp algorithm, right? So if two modulus they are same, still we need to compare the character, text and pattern again, but this is very efficient than naive Bayes because it is not like computing individual shift. It is just like using hashing, and if two values of the hash function they are not same, that means they cannot be equal. So we can keep on going. Look at here, this is one example. Suppose our pattern is 31415, right class? So if our pattern is 31415, we decide to use modulus as q equal to 13, right? So we take modulus 13 and its modulus is represented over here. This its modulus 3145, modulus 13 will be actually 7. So now we can compute all the modulus to get like this, but question is that we can compute this and all computation can be done. Look at here, its modulo is 7 and another modulo is also 7. That means 7 equal to 7. So we need to go to the text to check whether it is actually same or not. So 31415 is okay. So this is valid shift, but this is a spurious hit because its modulus is 7, but actually when we go to compare them one by one, it is not equal. So now question is that if we know this modulus, we know this 7, how to know the actually value of next valid shift? How to know the value of this? This is what Rabin-Carp introduced the concept of hashing. So how to get this equivalency? 31415, its value is 7 already, and then this is the digit, this 3 is this digit actually, and this 3 is actually, if you remember, h was congruent to 10 to the power m minus 1 modulo q. So this guy is going to be that h. So here pattern length is 5, so 10 to the power 4 modulo actually 13, this will give you 3, right? So that is what this is coming. So from this hash value, right, so you remove hash value of this is 7, remove this top digit 3 into h, and then whole multiplied by 10 is because of the radix is 10, plus 2 is the next value, right class? So this will be actually modulo 13. So what is actually coming over here? 7 minus 9 is minus 2, minus 20 plus 2. So this become minus 18 modulo 13. And we know that minus 18, 13 times 2, 26. So this can be 26 modulo 26 remaining 8. You see, this will be 8 because minus 18 modulo 13. So 18 plus 8, go to the next integer 26, and had it been it is 26 modulo 13, we will get 0. So but it is not 26, so how much is less? It is 8, so its value will be 8. So same thing, we can compute other value also in very quick manner, right? So you know what is actually this? If we compare the text and pattern, its value in a hash function, if both are same, then only we will go for the comparison. If they are not same, we will not go for individual comparison. So that is just like ruling out most of the matches. So this is algorithm. So third category of the algorithm, which is linear in time actually. not like, it is not like depending on pattern length. So this is known as Knuth-Morris-Pratt, which is known as linear time in the worst case, right? This is better than both of the algorithm. Also, although it was invented in 1977, but this algorithm is very popular. Actually, if you look at both the algorithms like Rabin Carp and Neo algorithm, they are not intelligent. So they will not think whether prefix was matching or not matching. So, but this algorithm is computing the information that how much you have matched actually. Look at this question. If you see, if we have this text and this pattern, so if you see, this is matching, this is matching, this is matching, this is matching. Correct matches, no problem. But had it been, if you are taking Neo-based algorithm, this will Neo will try another shift and again starting comparing triple A again. So that means number of comparison in Neo algorithm is more than Morris-Pratt. So what Morris-Pratt will say, that Morris-Pratt will not like compare them again because they are already matching. So it will compute prefix of a match, prefix of a pattern which has already matched. So that we can skip. Had it been, if we are applying the Knuth-Morris-Pratt, Knuth-Morris-Pratt will not match the 3 character at the beginning because Knuth-Morris-Pratt will not match them. Knuth-Morris-Pratt will match only this character, right? So you will see that this will involve pre-processing. Actually, this is trying to find out how many prefixes are there which has already been matched in the text. So this is computing prefix function pi, which store the information about prefixes of a pattern. We know that this is a prefix. Everybody know that. So what is prefix? So what is prefix function? It is taking pattern and it is matching. Its range is 0 to m-1. And most important thing is that what is pi q is the length of the longest prefix of p, that is proper suffix of pq. So look at here. Suppose your pattern is this, I is this. Suppose this is pattern. So pi 1, if you are talking about pi 1, so what p1 is a, its proper suffix is epsilon, null string. Proper suffix of a is null string. So its length is 0. So there is no problem. If you talk about p2 up to this ab, up to AB, what are its proper suffixes? So proper suffix is B and epsilon. B is not prefix of this pattern, and so only epsilon is prefix of this pattern, right? So again, if you go to this, what are the proper suffixes of pattern? Proper suffixes are A. Here up to this proper suffixes are A and BA only. So look at here, A is matching here, but BA is not matching. So what is its length? Its length is 1. Very correct, right? So same thing if you talk about up to 4. So what are the proper suffixes of AB? Proper suffixes. We don't care about full suffix. So its proper suffix are B, then AB, then BAB, right? So which one is the prefix actually? So B is not prefix, but AB is the longest prefix. What is its length? Its length is 2. Same thing if you talk about next one, ABABA, ABABA. What is its proper suffix? A, then BA, then ABA, and then BABA. 4 proper suffixes. So look at which one is the longest prefix, which is also prefix. Which one is the longest prefix from here? So if you look at here, up to this one, A is yes, its length is 1, BA is no, ABA is yes, its length is 3, BABA is no, so its length is 0. So what is longest? 3. So we compute it over here. This is very important, vital information to match the pattern against the text in the Knuth-Morris-Pratt. Same as here C class. Look at here, C not matching, AC, BAC, like up to BABAC, no prefixes are the no suffixes are the prefix of the pattern. So this is 0, right? Same thing here, A is prefix, CA not CA, no, not a prefix, then ACA not a prefix, none of them, so its length is 1. Let's have another example to compute the prefix, right? So look at here, this is very popular question, many times it has been asked in the AKTV examination. Compute the prefix function for the pattern. So what you should do, you just write 1 to 19 and then pattern write down from here to here. Look at here, pattern pi 0 will be always 0, pi 0 will always be 0 because only proper suffix is epsilon. And same thing, what are the proper suffix? Only B is proper suffix and B is not a prefix of this. Same thing here, A is proper suffix but A is only prefix, so its length is 1. What about this AB up to this? What are its proper suffixes? B, then AB, then BAB, right class? So you know what is the longest prefix which is matching over here? AB is the longest prefix which is matching over here. So its length is 2 now. Same thing we go here, B is not a prefix of at all, BB is also not a prefix, ABB is also not a prefix. Same thing, BABB is also not a prefix, its length is 0. Look at here, let us compute this value. Let's see this one. So A, what are its proper suffixes? Yeah, A is proper suffix, yes, then BA is proper suffix. A is proper suffix which is matching here, yes, its length is 1, then BA no, and then ABA, yes, it is matching here, yes, ABA, it is matching here, its proper suffix, its length is 3, we are done up to ABA, right? And then BA is not prefix, yes, BA, then BABA is also not a prefix. So you will see that none of them will be prefix and we have to find out up to this. So its length is 3. Same thing here class, if you go here, its value is 8. What are the proper suffixes? First one is B, not a prefix. BB is not a prefix. ABB is not a prefix. Yes, not a prefix, not a prefix, not a prefix, right? We are done up to this. Same as BABB, not a prefix, very good. And then BBABB is also not a prefix. Same thing here up to ABB, then ABB. Look at here, no, it's not a prefix. Same thing, go now and then ABB, yeah. Yes, we are done up to no, not here. Look at here, we started from here, yeah, ABA, ABB, no, ABB, yes, here. So what is its length? Here, from here, ABA, if you go here up to this, ABA, ABB. So what is its length? 3 plus 2, 5 plus 3, 8. You will go back, you will not get any prefix. So how this is going to be used in matching actually? So let's consider a text. Just like we started with this, if you remember Naive algorithm, this will compare this and this. Compute its pi function. This is pi function of 4a. You see this 0 and then 1, 2, 3, because we are getting proper suffix which is prefix. A matches, AA matches, and triple A also matches. So we get it here. So we will start from 1 and 1. I is 1. I will be responsible for this and J will be responsible for pattern. So initially I will be 1 and J will be 1. We started with 1, 1. There is a match. Then we will increase I and increase J. Very correct, right? So now I become 2 and J become 2. That means this is going to be compared. Yes, both of them they are okay. So then increase I and j. Now I and will become 3 and j become 3. Very correct. We compare with them, yes, they are okay, they matched it. So that means again you need to increase I4 and J4. Very correct, right? Okay. So that means I is 4 and J is 4. We are going to compare them. They are equal again. So again you have to increase I. In case of equality, we have to increase I and J. So now here I become 5 and J become 5. Now any time J become m plus 1. If you remember, there was a complete match here. There was a complete match here and pattern length is 4. So any time if you look at here, J is equal to m plus 1. That means pattern length plus 1. This means there is a complete match. We have to reset J, right? So how to reset J? That is the typical things here. J will be whatever is pi, J will be pi j minus 1. So what is J? J is 5, pi 4, 5 minus 1 become 4. And look and consult pi 4. 1, 2, 3, 4. Pi 4 is 3. That means it is very giving vital information. That means from beginning we are not going to compare 3 character. We do not match first 3 character, right? So that means they are not going to be matched again. That means they are already prefix of the matched. So what you are going to compare? Only this character you are going to compare. After I become 5. 1, 2, 3, 4, 5. That means we are just comparing one character. It is unlike unlike Naive algorithm, which was comparing every character here, because this is already matching, so no need to go there. And you see this is prefix is 3, so we have to skip the 3 character and J will be 4. Look at here, 1, 2, 3, 4. 4 matches will be there. Again T and PJ matches, that means yes, they are matches. So J become 5 again, yes, means complete match again. So right, reset here. Look at here. Again there is a complete match. There is a complete match, right? So we have to reset again, right? So J is m plus 1. So again pi j was 5, pi 4. Pi 4 is again 3. Look at here. Pi 4 is 3. That means again we are not going to compare first 3 character, right? So matching will start from 4th character, right class? This is going to be matched and we got mismatch again. So since there is no matching again, and what was J? J was 4. So we have to consult, in case of mismatching, we have to consult pi j minus 1, pi 3. So what is pi 3? Pi 3 is 2. So that means we have to skip first 2 character and comparing with the next one. Look at here. We have to skip first 2 character. We skipped it already because they are already here. So again J is 3 now. J is 3. And again there is a mismatch. That again pi, consult pi 3 minus 1, which is 1. Pi 1, pi 2 is 1, pi 2 is 1. So again so what will happen? Again one character is not going to be matched. Look at here. That means we are not going to match it again because of this pi information. So again you need to match it. There is a mismatch. So what was J class? J was 2. So pi 2 minus 1 become 0. Pi 1 become 0. So we have to reset everything. And since I was 6, I will remain the same. Look at here, I will remain the same and J will become 1. We have to restart again. So that means every character need to be matched again because this information become 0. So anytime this information become 0, you have to start from the beginning. This is very good algorithm. At least it is intelligent and finding out the solution, and it is ignoring already matches. Look at here. It is another example. Consider AB. This is your pattern. Why I have taken AB? So that you should see these some suffixes are already prefixes. Look at here. This is the matching and this is matching, right? AB one match and AB. There is a overlap. We have overlap. So same technique, we will design the pi function for this. Look at here, B is not prefix, it will be 0, it will be 0, A is prefix. BA is not prefix, it is 1, AB is prefix. So we get this pi function, right? We will start from 1, right? We will start from 1 and 1 again. This, as I said, this will be, I will be accountable for this and J will be accountable for this, right? So I is 1 and J is 1. Look at here, there is a mismatch and J is already 1. It must be greater than 1 in order to consult the pi. Since it is already 1 and you look at here, pi 1 will always be 0. So no need of every time you have to start from J equal to 1. So for this one to work, J must be greater than 1. Only you need to consult the pi function. Otherwise, no need to consult the pi function, right? So that means I is still 2 and J is still 1. Look at here, compare them. They are same. So I is 3 and J become 2. Same thing here, matches I4, J3. Again matches I5, J4, right class? And then again matches I4, I6 and J5. Look at here. J is 5, that means it is equal to M plus 1. That means there is a possibility of the complete match, right? So you need to compare J pi, whatever is J, actually pi J minus 1. So pi J is 5, pi 4 will be 2. It will tell you that 2 matches are already there. So in next matches, please don't compare these 2 matches, right? So you see here they are already matches, so we are not comparing them. So matching will start from J equal to 3, right? So you know J equal to 3 because J is 2, whatever answer is coming you increase by 1. So this is matching, this is matching. Only 2 comparisons are made. Had it been neo algorithm, you will compare 4 matches. So this is better than the other algorithm. So same thing here. Look at here, I is 8 and then so J updated by pi 4 again 2. So this will continue. So this has come. So as I promised you that only I am going to cover 3 algorithm, naive algorithm, Robin, Carp and KMP. Only these 3 algorithms are in AKTU syllabus. Rest algorithm will cover in the next lectures. That will be in advanced like string matching. So thank you for watching.